The next topic is polymorphism or generics. And by the way, one thing I should say is that as you look at CLUE, and if you think about it with respect to modern programming language, and especially Java and C#, but even other languages that have data abstraction mechanisms, one thing that really strikes you is how similar it is. Okay, but it's similar because CLUE was there first. And these other languages have borrowed from it, as they should, because that's the whole point of research, is that you build on the past in order to go to the future. Okay, so as I said, it's not enough to have a set of integers. You really want to have a set of t, where t is an arbitrary type. And so here I'm showing you, I just changed the header, so I have a type parameter. And down here I'm showing you a use. When I use it, I say, well, for this one I mean it's an integer. Okay, however, it turns out that there is one very hard problem with generics, and that is, in general, not every type makes sense as a parameter. So even for sets, not every type makes sense, because sets fundamentally require that the type of the set element have an equality relation, so that you can ask the question when an element's added to the set, is it there or not? Or so when somebody says, is this element in the set, you can say yes or no. And not every type has an equality relation. At least not, today Java says every type has equals. Of course, they don't actually say what is equals really supposed to mean. And in general, equality is just a simple example of what I'm talking about. Other kinds of types will have more constraints that definitely are not mandated by the programming language. So this was a big worry to us. How do we capture the fact that not every type can be used to instantiate, as I'm showing you here? And ultimately, we came up with the solution of the where clause. So what we did is we added to the header of a parameterized cluster a where clause that stated the constraints on what operations the type being used as a parameter had to have. In this case, we say it has to have an operation named equals, it takes in 2 t's and returns a boolean. And we could have required several other things if we wanted to. So that was our solution. And once you have that, if you go back one slide, you can see that you can do all the type checking you need to do. Because when you encounter an instantiation, like what I have at the bottom of the slide, the compiler says, well, does this type that's being provided as the actual parameter, does it have the operations that were required? And it'll either accept it or not, depending on whether it does. And when the compiler compiles the set cluster, it can use those operations. They can be used inside the code, and it knows exactly what operations of the parameter type are allowed to be used in there. Okay. Go ahead, one more. In fact, one more. Okay, exception handling. As I said, exception handling was not necessarily there in your language at the time, and in fact, there was a great deal of confusion about what exception handling ought to be about. And John Goodenough wrote this paper in 1975, in which he kind of laid out the state of the art as it existed at that time. And what he pointed out was that there were two things that people were arguing about. First of all, they were asking the question, should it be a termination model or a resumption model? Termination model is what we use today, where the procedure terminates with an exception. The resumption model says it throws an exception up to its caller, the caller might do some stuff, and then control goes back down into the procedure, which continues doing its job. Okay. The second question was, how do you specify what the handlers are? So when an exception happens, how do you identify the code that's supposed to run in response to the exception? Today we use call site handlers, so you can tell by the syntax of the caller exactly where the exception is supposed to go. Then there were other proposals, like maybe there's a module off on the side that handles all exceptions or something like that. Okay, so this was the landscape. We wanted to have an exception mechanism. We wanted one because from a program methodology point of view, it's very important to write your procedures if possible so that they are total, so that they will not blow up or misbehave no matter what set of legal arguments is passed to them. However, of course, that doesn't mean they can necessarily do the same thing for all the arguments. And so you need a mechanism for handling the cases that you can't handle in the normal way. And you do not want that to be what's done in C, or used to be done in C, of folding it into a result, because the problem with that is people ignore those results, and then the error shows up much later in the program, and you can't figure out what's going on. So you need exceptions as a way of conveying this information. So I'm not going to really spend time on this. We came down in Clue with the design. It's like what you see in all modern languages. We use termination model. We use call site handling. Go ahead, one more. However, we did one thing in Clue that I really wish everybody else had done. And that is we had a resolution for the problem that happens in any language where there's an exception mechanism. Namely, what do you do about the exceptions that are not supposed to happen? Okay, so if you think about writing programs with an exception mechanism, supposing I just check that the set is non-empty, and then I call an operation on sets like the one that returns some element of the set, and I get the empty exception. What am I supposed to do with that? What does the programming language say I'm supposed to do? So think about Java. Java mostly says, you better write those handlers anyway, otherwise the compiler's not going to like it. What this means is your code is full of your worthless stuff, okay? What C# says instead is actually worse. It says, do whatever you want, okay? The problem with that is then you never know what the interfaces are, because this means exceptions go shooting up the stack, and you never know by looking at the header of a procedure what exceptions it might raise. Okay, Clue had a third position. It said, we know what exceptions are supposed to be raised, and we will recognize in the compiler if one of them isn't handled, and we will turn it automatically into a special exception named failure. And therefore, now you know what all the headers are, because every procedure can have a failure exception in addition to the ones that are stated explicitly. And the failure exception is actually used for these weird cases where I just checked for empty, and yet I got the empty exception. So these are typically going to shoot way up in your code to some sort of checkpoint where you restart and then continue on. Okay, here's my last story about Clue, and this one is actually interesting, and it's the one place where I went beyond the minimality argument. Okay, so we were very worried in the design of Clue about how people could write programs of this sort. Typically, many data types are collections. When you collect things into a collection, it's because you want to do something with them. You're going to iterate over the collection, you're going to print them, you're going to add them, whatever it is that you want to do. So, how do you express this kind of program? Well, of course, you don't actually need any special mechanisms, because here are two ways you could do it without anything special, but they're both bad from a programming language design perspective. The first one is you destroy the collection. Okay, so I keep taking elements out of the set, and when I can't take any more out, then I know I'm finished. The trouble is, maybe I actually wanted to use the set twice, and so that's not a great solution. The other thing you can do is you can complicate the abstraction. I can turn the set into an indexed set. So I can talk about the first element, the second element, and so forth, and then I can iterate using that notion of indexing. That's, in some sense, actually worse from a programming language design perspective, because what it did is it forced a programmer to turn something simple into something more complicated. And really, programs are complicated enough already without having to add more stuff. Okay, so this is where we were when I took my team to visit at Carnegie Mellon in, I think, the summer of 1975. I took my 3 graduate students, and we went to Pittsburgh, and we met with the group working on AlphaArt, the other main work on programming like abstract data types that was going on concurrently. And they told us about their work on generators. And, think about Java generators. That's what they were working on fundamentally. The idea was you had a sort of an auxiliary type. It had some operations, you could get started, you could ask for the next one, you could check whether there was something else, and they linked it into a for statement so you could use it through the for statement. So we could see that this was a solution. We just thought that it was kind of inelegant. And so on the airplane ride going back to Boston, my student Russ Atkinson invented iterators. And for iterators, think what you have in C#. Okay, you have to show the next slide. An iterator is a kind of a special kind of procedure where it yields a bunch of results, and when it finally terminates, then it's done. It can be called only through a for statement. When you get started in the for statement, you call the iterator. Each time it yields a result, you run the body, and then when finally the iterator terminates, at the end of the body, go back into the iterator right where you left off. So inside the iterator, we're keeping track of the state, so you don't have to worry about where you were last, you just pick right up. And then when finally the iterator returns, the loop is over. Okay, so it's a very straightforward mechanism, and you see these mechanisms in modern programming languages. Just like iterators, they've gotten a little fancier nowadays, but this was the basic thing that we came up with in Clue. Now, here's a couple of interesting points about Clue. We knew, first of all, that this was a 95% solution, that there would be cases where you would like something more complicated than this. We decided that's okay, you can build a generator if you need to, but it's better to have a simple, straightforward solution that works most of the time than to have something more crafty that solves the last 5%. The other thing was we had a very good implementation. I haven't mentioned this before, but we thought about implementation all the time. We were building the compiler as we worked on the language. We actually did an interesting little bootstrapping experiment where we first wrote a first compiler, a very simple subset of the language in a Lisp dialect, and then after that we just keep writing the compiler in Clue. This was actually a very good test case for us because the compiler is a pretty complicated program. And so we had a very good implementation technique for this. The compiler turned the loop body into a procedure, passed the loop body to the iterator as an argument, then the yield just turned into a call, and finally when the iterator was finished, you were done. Okay. But you know, generators are in some sense a coroutine-like structure where you can keep going back and forth between the user and the generator itself. And they're much less nice to use than iterators because you have to take the state of the iteration, put it into the instance variables of the generator, and then remember next time you're called where you left off by using those variables. Whereas with iterators, it's just right there in the stack. Okay, so I'm finished with Clue, and I'm going to not spend too much more time talking. What happened was I finished the design of Clue in the late 1970s. And at that point, I was thinking about what to do next. And I could see one path forward, which was to sort of continue working on Clue and maybe think about commercializing it. The world was different then. Today, I would have put it out as open source. In fact, it is still available and people can get it. And nowadays you put stuff out as open source and it develops a life of its own. But that was not how it was then. Then people wanted programming languages that came from vendors so that they knew they had support and so forth and so on. So I decided not to do that, although I've always been a little sorry that I didn't. But what happened was I saw a fabulous research opportunity because the ARPANET was there and people were starting to send email, they were doing file transfer, they were doing remote login, and they had a dream about writing programs that ran in a distributed manner with pieces of the program running at different nodes of the network, but they had absolutely no idea how you would write those programs. So I thought, here's a great research opportunity. So I moved into distributed systems, and I've pretty much stayed in distributed systems ever since, although I've always continued my interest in programming methodology. Now, I'm not going to talk about the work I've done in distributed systems. Argus was the first project that I did there, but I went on to work on replication and storage and so forth and so on. What I do want to do is talk about one little last piece of programming methodology work that I did, and this is this work on type hierarchy. So what happened was I was invited to give the keynote at UPSLA in 1987, and I thought that this was a really good opportunity to go back and look at the literature in the object-oriented world, which had been working very independently. It was almost like an East Coast, West Coast phenomenon, because Alan Kay was developing Smalltalk on the West Coast, I was working on abstract data types on the East Coast, and neither of us was paying a lot of attention to what the other one was doing. So I thought, okay, I'm going to go and see what's been going on with object-oriented languages, and so I started reading papers in the literature. And what I discovered was that in those days, there was a single notion of inheritance. There were classes and subclasses, but they were being used for two quite different things, because they were being used as an implementation technique where you could take a piece of code, you could make a subclass and add a little bit of extra behavior. And they were also being used for type hierarchy as a way of classifying behavior-related types. And these two things are quite different, and yet they were being done by the same mechanism, and people were really very confused. So I remember reading a paper in which somebody said, well, stacks and queues are really subtypes of one another. And the argument was, well, they both have an operation to add, they both have an operation to remove, and therefore they're really the same. Okay? And that's screwy, if you think about it. Because if you write a program that expects a stack and you get a queue instead, it's unlikely to actually act the way you expect it to act, because FIFO versus LIFO is actually a big difference in behavior. So this led me to invent what came to be called, so it wasn't well understood, go on one more, what came to be called the Liskov substitution principle. And what I said in my keynote at OOPSLA was what I have here on the slide. Objects of subtypes should behave like those of supertypes when used through the methods defined by the supertype. So it was okay for them to have other methods that did other stuff, but if you limited your use of them to the supertype methods, then you should not be able to tell that you were dealing with a subtype. It should behave exactly as the supertype said it would. Now, this came to be called the Liskov substitution principle. I didn't stand up there and say, here I have the Liskov substitution principle. What happened was I got an email sometime in the 90s, maybe around 1992, from somebody who said, can you explain to me whether blah, blah, blah is the correct interpretation of the Liskov substitution principle? So this was the first time that I knew there was such a thing as the Liskov substitution principle. And in fact, there was a huge community, I discovered, arguing about the nuances of the Liskov substitution principle. So it was fun. Okay, so I'm just going to conclude with a little bit of final remarks. So the first thing is, I learned something amazing when I got the Turing Award. So my husband was online every day looking for the newest news, because I mean there's just stuff all over the internet. And one day he found this quote by somebody who'd written it, in which they said, what did she get that award for? Everybody knows this anyway. And if you think about this, this is a huge compliment, because what happened was the world changed. Everybody did not know about modularity in the days when I invented these ideas, but by the time I got the award, this was so built into the way we build our programs that everybody didn't know it. It was quite amazing. So the world had changed. I had not been thinking about this at all. I mean, I'd just been doing my work in distributed computing, and I discovered this thing. And I actually discovered also my students didn't know there used to be a different world, so it was really quite interesting. Anyway, that's that. This is now. And what I put up on the final slide were just some research topics that appeal to me. All I'm trying to say in the end is, there's still a lot of life left in computer science. I happen to have gotten in very early, and I felt that was very lucky. But there's a lot of interesting research going on today. And I just put on the slide research that interests me because I'm in the systems area. I always thought it would be wonderful if somebody came up with another abstraction mechanism with the kind of power that data abstraction had, because what that did is it raised the domain of discourse so that we could cope with more complicated programs and yet keep the complexity under control. And if somebody came up with another invention of that power, then it would enhance our ability to build programs in a way that we can't really foresee. The main reason I don't do work in programming languages these days is because I don't know what that abstraction mechanism is, and I'm not too interested in pursuing it in the absence of an idea like that. But other people, might find something. One problem that's a very pressing problem for us today is what to do with the massively parallel computers. God did not say that when Moore's law ran out, this meant that Intel had the right to sell us computers with thousands of cores. And in truth, it is not clear that this is going to be a successful enterprise. It's not that it isn't an interesting problem from the hardware perspective. In fact, it's a wonderful playground for computer architects. It's also very interesting from the operating system's perspective. What should your operating system be like so that it would run efficiently on that kind of architecture? It's an interesting problem from a programming language perspective, although, honestly, the history of programming languages in the concurrency domain has not been really stellar, because it's a very hard problem. But the real problem is, can we write programs that use these architectures effectively? And I'm not talking here about embarrassingly parallel programs. We know there are graphics processors that can effectively use lots of different cores. We know that we can make use of a few cores inside of our machine. We know all our machines have several cores in them, but they're being used in a very disconnected way. Each one is being assigned to a different task. Can I take a database system and use thousands of cores to run the database concurrently? That's the kind of problem I'm interested in. Can we actually use multi-core machines to solve those kinds of problems where there are synchronization issues, and you have to work them out? What model of computation should we use? How should we proceed with these machines? So I think that's a very interesting area of research. And then I actually am more still in the distributed system domain, and what strikes me there is, we're in the age of cloud computing, where in some sense the internet is a computer. You can put your storage out there, you can run your programs there. But if you look at the commercial offerings that are available, what you see is that the semantics isn't very good. So the storage doesn't have exactly the properties that you think it should. The computation, there's these problems of leakage and security and so forth and so on. So there's a rich source of research problems here to go from where we are now to where we really would like to be to make that a utility that everybody would use. And that's the end.